Welcome, pre-calc honor students, to 4.4, periodic functions, and also stretching and translating graphs. We're going to start by talking about these ideas of periodic function. A specific definition for what a period is. P is the period if for all x in the domain of f of x plus p equals f of x. So if you go p further to the right, you'll be at the same y value. The smallest such period of a periodic function is called the fundamental period. And that's usually what I imply when I say find the period of the following function. That's the smallest such period. So let's take a look at this on GeoGebra. Here's a way you can generate a period. Right now, this function is not periodic. It might repeat these values at a and d, but if you say the period is 5, 1, 2, 3, 4, 5, and you go here, f of 0 goes to 2, but f of 5 does not go to 2. It doesn't exist yet. So we can make a copy. We can highlight the entire graph and then translate object by vector. So I select an object, this object, I select this vector. There. And it has made a copy of it, all slid over 5 to the right. Now we start seeing the periodicity, and we can continue to do that as we just select successive objects here. Now we can select this object, apply this vector again, go to the next one. Apparently I didn't catch this object here, so there we go. And we can keep doing this ad nauseum. And here we go. And didn't catch that part, so there we go. Now we have a periodic function with a period of 5. So that's a little illustration of periodicity. And so now, if you didn't know what the period was, you could look at this and look at what you have to copy over and over again to get the whole function. And it would be this section. You'd see it'd be 5 long. And whether you count it from here to here, or from here to here, so we keep seeing this gap of 5. Okay. Now, we also have some things on a function called amplitude, minimums, and maximums. And the amplitude is basically how tall is the function. But to get this, it's how tall is it above its midline. So you have to take the maximum minus the minimum and divide by 2 to get the amplitude of the function. So let's apply this on the one we just looked at. What's the amplitude going to be? Let's pause while I get a picture of this. So on the function we just graphed, the amplitude is equal to the maximum, which in this case is 3, minus the minimum, which is -3, all over 2, 6/2, 3. So basically the x-axis itself acts as sort of the midline for the function. And we see we're going as high as 3 above and 3 below the function. All right, now what happens if we try and change the period and amplitude function? How do we do it? So let's look at a different function now, something you're all familiar with, the sine function. And first of all, let's see, what is the period of this sine function? Is it this pi, this vector, or this vector? A lot of people mistakenly think that since, well, you keep on hitting 0 here, it's 0, pi, 2 pi, 3 pi, that the period is pi. But if we do our same vector translation here, and we move this object A by this vector dE, you can see how it's not working. That is, when we're at the zeros, yes, it looks like the period is pi, but here at the nadir, no. And here at the peak, no. So that is not the period. It has to work for all x in the domain. So if instead we delete that, and now look at translating a vector from here, A using this 2 pi, 2 pi. Now you see we're staying on the function at the peaks, at the zeros, and at the nadirs. See how A prime? That's what we mean by f of x and f of x plus p. Okay. Now, what about some of the shrinking things and so forth on this? What happens if we put a 2 in front? Now watch what happens in red here. It doubles the amplitude. Now instead of amplitude of 1, we have an amplitude of 2. Notice the zeros had stayed in the same spot. And the period has stayed the same. Now if instead we double the inside, it actually affects it horizontally and shrinks it. So the period is shrunk by a factor of 2. The amplitude has remained unchanged. Okay? So 2 interesting effects on there. Let's sum those up then. Let's see what those mean in our picture. And so now we can see the effects here. That we've got a periodic function, a sine wave, with a period of 2 pi and an amplitude of 1. And now if y equals c times f of x, that's what we're doing here with the g function. The period stays the same, but the amplitude gets doubled. Then, if we do f of c of x as a period of the period divided by c, with the sine 2x, the period got cut in half, and the amplitude stayed the same. All right. Now we're going to try and make sense of a whole mishmash of possible graphing effects by looking at our last GeoGebra of the day here. Simple function. I'm not even going to tell you what the rule is, but let's just look at y equals fx, the black function. Now let's look at this first effect. Y equals negative f of x. What happened here? Well, it looks like it got flipped over the x-axis. Even though we're affecting the y's, we flip over the x-axis because to do so is to change the y coordinate. Keep the same x coordinate, change the y coordinates. So we can see when effects are outside the functional notation, they affect the y's. And when they're inside, they affect the x's, as we see in this next example. Here's f of negative x. F of negative x. And it has been a flip over the y-axis now. Here we have f of x minus 2. That is what baffles students sometimes, because x minus 2, it's actually going to the right 2, not to the left 2. So this is an example of a horizontal translation. And because this function is basically compensating for this. Note the difference with L, which is f of x minus 2. It's outside the functional notation, so it brought everything down. So in one case, it looks like it's doing what makes sense. That is, y's are equal to the old y's minus 2. But in the other case here, it looks like it's backwards. It's all because of the nature of us always solving for y as a function of x. So it's on the opposite side of the equation, this effect, from the variable it's affecting, so it does what you'd expect. The y's are the old y's minus 2. When it's on the same side of the equation, this effect is on the same side of the equation of the variable we're affecting. It does the reverse effect. So instead of shifting to the left 2, it actually shifts to the right 2. So y equals f of x minus 2. We'll see this too as if you were to solve for x as a function of y. You'd have x minus 2 equals f inverse of y. X minus 2, x equals f inverse of y plus 2. And you'd see that when you put it on the same side as the y, it's actually doing the reverse effect. It's actually moving x to the right. Let's put those two away and see what some of our little absolute value tricks do here. There's y equals the absolute value of x. When you take the absolute value of the whole function, you're just going to flip the stuff that was below the axis and put it above the axis. And then when you take the absolute value inside the function, you're going to leave the stuff to the right of the axis alone because the absolute value of x is basically no effect if x is positive. If x is negative, though, this stuff disappears. And the negative stuff over here acts like the positive stuff over here. So we basically ignore the stuff to the left of the y-axis, and we reflect the stuff to the right of the y-axis over the y-axis for absolute value of x. Okay? So let's get these effects sorted out here. Got them all in a jumble down here somewhere. So what's reflecting in the y-axis? That's when we switch the roles of x and y. There you go, right there. X equals f of y. Reflected in y and y equals x. Reflected in the x-axis, we actually take, that's flipping this one right here. Y equals negative f of x. Reflects it in the x-axis because you're actually changing the lines. Reflecting the y-axis is f of negative x. And here in the fine print is that absolute value of f of x we talked about. We reflect in the x-axis when f of x is less than 0. That's basically this transformation. But when f of x is greater than 0, you ignore the absolute value. Now, stretching and shrinking. This is always kind of confusing. Let's see if I can't clear it up for you here. First of all, this y equals c times f of x is going to be effect on the y because you're multiplying outside the functional notation. When c is greater than 1, then it's going to be a stretch vertically. If c is less than 1, it's like dividing, so it actually shrinks it vertically. So this will be shrunk vertically. Now, when we work inside the functional notation, you're affecting the x's, but it does the reverse of what you expect. So this, when c is greater than 1, instead of stretching x, it actually shrinks x horizontally. So this is shrunk horizontally. And then the reverse here, it's stretched horizontally. See, between 0 and 1. Finally, this leads our basic translation. It's not a flipping or anything, it's just a moving over h and up k. I mean, in this case, and up k. H units horizontally and k units vertically. We see this all the time in a lot of our forms for the circle and ellipse and hyperbola, and for the parabola. Flange out.